Hello and welcome once again to the 8-bit CPU. And in the last episode we had a look at the hardware of the control unit. And so the control unit, its principal component are these 4 EEPROM chips. And so the control unit is basically a huge combinational circuit which takes as its input the 8 bits corresponding to the currently executing instruction or its opcode, which are these 8 bits here. It also takes a micro time value, which is a maximum of 3 bits long, which is provided by this counter here, which simply counts on every clock pulse. And then finally, it takes in 2 bits from this 4-bit flags register. And in the last episode, we talked about how the carry bit is always available to these EEPROMs. And then the final bit is a result of a combinational logic of these 3 flag bits together with some selector bit which we can set in the opcode of the instruction. And so we have a total of 2 plus 3 is 5 plus 8 is 13 input signals which are connected to the address lines in parallel of all of these EEPROMs. And the outputs of the EEPROMs are connected to these 27 different control signals which we have, which are routed through all of these yellow wires all the way across the CPU to the various data handling and manipulating components of the CPU. And so these control signals, they manage the various other components, the register and the ALU memory, for example, to manipulate and move around the data inside the CPU in order to accomplish whatever this instruction is supposed to do. And so today, what we're going to have a look at is how that translation is implemented. So how do we come from this instruction opcode together with the timer and the flags to the actual control signals which we need to correctly perform the operation of the instruction represented by this opcode. And so to do that, we need to program these 4 EEPROMs. And so that's what we call the microcode of the computer. So the microcode is exactly that. It's the code which translates the instructions which the programmer writes in assembly or in machine language, these here, into control signals which actually perform the data manipulation. And of course, since these are EEPROMs, we'll be using our EEPROM programmer, or in fact I already have used this EEPROM programmer here, which is based on this Arduino Nano. And so we already had a look at that in our episode about the digital display. And we saw in that episode that we can write, using the Arduino software, we can write a small library which allows us to very simply access the read and write operations to an EEPROM using this EEPROM programmer. And so we'll be reusing that library once again, but then this time to program the microcode into these EEPROMs. So let's stop the computer at an appropriate moment. This looks like an appropriate moment. Just to have a look and to make sure we understand exactly what we're talking about. So I've halted the clock for a moment, and so at this moment you can see that the micro timer is on time 0. So this 3-bit value has a value of 0. This instruction register contains this particular opcode, which is in fact 2. The program counter contains a value of 16 at this particular time, so that's that 1 single bit, and all of our flags are 0. Now the program counter doesn't directly go into the EEPROMs, of course. The program counter will be used during the first few cycles of the instruction execution to go and fill this instruction register with a new instruction, because we do have an instruction in here, which is this. If we try and remember how our instructions are encoded, so 00 means move, and these 3 bits indicate the A register, so that's the destination, and these 3 bits, which correspond to a value of 2, represent the C register. So in fact, at the moment, this is a move into A from C. And so if we look at our program, there is indeed a move into A from C instruction, but it isn't located at this address. It's in fact located at the address before it. And so what we're seeing right now in our instruction register is still the opcode from the previous instruction. So although we are now going to start executing the instruction at address 16, our control unit doesn't know what that instruction is yet. So what's in the instruction register right now is still the opcode of the previous instruction. And so as we discussed in the last episode, the first two cycles of the instruction, which we're going to execute, they will in fact always do the same. We will go and push out the contents of the program counter onto the bus, and so here is that same 16, and we'll be writing them into the memory address register, which is here on the next rising clock edge. And so these four EEPROMs during time t0, so whenever these three address lines are 0, the contents of the opcode here and the contents of these flags should be totally irrelevant. It should always be outputting these two and only these two control signals. So that's one of the first things that our microcode will have to take care of. So all right, so when he executes that 16 will appear in here, and so there it is. And at the same time, after that for rising clock edge, the clock edge fell again, of course, and when it fell down, then this counter moved up to a value of 1. And so now we're on the microcycle number 1, and so here too, we still don't know the correct value of the opcode that we should be executing right now, because it's still in memory. It's located in program memory. So we need to get that out of program memory into the instruction register. And so for a micro time value of 1, we should also always output exactly the same control signals from our EEPROMs, no matter what the contents of the instruction register or the contents of the flags register. So in this case, what we need to do is we need to enable memory out onto the bus. So here's RAM, which is the contents of RAM which are pointed to by the memory address register, which we loaded in the previous cycle. So they're out on the bus here, and they should be written into the instruction register. So they will appear here, and then they will be able to drive the opcode input lines of these EEPROMs for the following microcycles. Not only that, we need to make sure that we select program memory. So the program memory control signal is also on. And so the byte which we're outputting onto the bus is in fact the byte located at address 16 in program memory, not in data memory. And then finally, we want this program counter to increment by 1, so that when this instruction finishes executing, we'll already be set up to start executing the next one. And so the final control signal, which we need to assert on this cycle number 1, is the program counter count signal, and so that will cause this to increase by 1 on the next rising clock edge. So we're right, when that happens, that will increase, and that will come into here on the rising clock edge, and on the falling clock edge that will increment by 1. So there we are. Now, as we can see, the correct opcode for the instruction at address 16 is in the instruction register. And so from time 2 to potentially time 7, now the particular control signals, which we will program our EEPROMs to send out based on these combinations, well, they will in general depend on this opcode and possibly even on these flags. Now this is a very simple instruction. It's a move instruction from B into C. And so to do that, we really only need to do one thing. We need to enable the contents of the B register onto the bus. And so we have this B register enable signal, control signal active. And at the same time, we need to activate the C register write signal. And so on the rising clock edge, these contents of the B register, which are already on the bus, they will get latched into the C register on the next rising clock edge. And then a final signal which we're asserting is this timer reset signal. Also, as we discussed in the last episode, whenever our instruction has finished, and so this really is the last thing we need to do to complete the move into C from B instruction, we can reset this timer so that we get ready for the next instruction, and that way we avoid cycling through the next values 3, 4, 5, 6, and 7, which don't need to do anything. So we save some instruction cycles. And so that if we execute this final time 2 set of control signals on the next rising clock edge, well, that will complete the execution of this move instruction. So let's just do that. And so now this has been reset again, and we're now ready to go and execute instruction 17. And so hopefully that gives you an idea of the job that the microcode needs to perform. So it needs to translate this time value here, 3-bit time value, this opcode value, and these flags values into a valid set of control signals. And so that's what we'll be looking at. So here we are in the Arduino development environment, and this is I've loaded the program which we'll be using or which I've used to program our control unit EEPROMs. And as you'll hopefully remember from the episode on the digital display, we wrote a small library here with slightly higher level functions to be able to read and write to our EEPROM chips easily using the EEPROM programmer that we built. And so we have some higher level functions here, an init function, then read, write, and dump from the EEPROM. And so we wrote a C++ header file, and then we wrote an implementation here in C++, which in fact uses the way we wired up the Arduino and the EEPROM on our EEPROM programmer to accomplish these reads and writes. And so to understand the details of that, I would refer you back to that video on the digital display. And but so in this episode, we'll simply be using that, and we'll be using it by including this header file in our microcode program here in the Arduino editor, and that way we'll have access to these functions, and we don't need to worry about the details of how those are implemented. So right, here is our program to program the EEPROMs to insert the microcode into our 4 control unit EEPROMs. And so since we have 4 of them, and in effect we want to provide 27 different control signals, that's after all the job of the microcode and of the control unit, we'll be dividing those 27 control signals over the 4 EEPROMs. In fact, we already have, that's the way we wired up our control unit. And so in this program, we'll be representing that by what I call a signal word, which is a 32-bit word, which will contain all of the bits, or all of the control signals, which are distributed across those 4 EEPROMs. And so I've assigned bit values in my signal word to the different control signals, and so I've assigned them obviously by grouping every single EEPROM together. So these first 8 bits here, these least significant 8 bits of my signal word, well, those are all the output bits on the EEPROM number 0, on the first, or the EEPROM which is furthest to the right on our computer. And so that contains all of these control signals. So that's the ALU carry in, the ALU S0, 1, and 2, the ALU B register, or Z, the ALU write and enable, and then finally it actually also contains this program counter count signal. And so that's those are all the control signals which will finally end up on the EEPROM number 0. Then bits 8 to 15 of my signal word here, well, I've assigned all of those to EEPROM number 1. So that's the EEPROM with the second EEPROM from the right. And so that will contain all of these control signals. And so those have been wired up that way. And so bit number, output bit number 0 of EEPROM number 1 is in fact, output bit number 0 is in fact bit 8 in my signal word, and that will be routed to EEPROM number 1. And so we'll be writing all of these signals to EEPROM number 1. And EEPROM number 2 is contained here in bits 16 to 23 of my signal word. So that will contain all of these signals from register C write up to the halt signal. They will be sent out on EEPROM number 2, which is the third EEPROM. And then finally the fourth EEPROM, which is EEPROM number 3, will actually only contain 3 signals. So this memory write, memory enable, and then the timer reset signal. And so I've assigned timer reset on that EEPROM to output bit number 7 of the EEPROM, which is the 31st bit, or the most significant bit of my signal word. And then these 2 signals will be controlling the RAM memory write and enable signals. And so that's how we're going to access the different control signals inside of this Arduino program. And I've defined a series of handy constants here. So for example, the control signal, so for example this one is the stack pointer enable signal, and so I've defined that to be a 1 shifted left by 9 positions, because it's in fact in bit position number 9. So if we use that constant at any point, well, that will be in binary, that will be a 1 followed by 9 zeros, and so that will represent, if that were the complete signal word, well, then that would represent every signal off except for this signal. And so if we OR several of these constants together, for example, A register write and B register enable, if we were to write RAW or RB enable, well, we'd be enabling the binary bits number 15 and bit number 12, and so we'd be we'd be ORing together this signal, and so that would represent microcode, which performs a B register enable and an A register write. So that would already be good microcode somewhere, for example, in the move into A from B instruction. And so using these constants, we can then write our microcode in a slightly more readable way. You'll notice that most of these have an underscore, and of course that's deliberate, because we want to remember that very many of these signals are in fact active low. And so in the final byte, or the final data which we'll be writing to the EEPROMs, we need to remember that if in our signal word that bit position is off, we actually need to write a 1 into the EEPROM. And so an easy way to remember that in this code is to simply name the constant with an underscore, and that will hopefully constantly remind us that those particular bits need to be flipped just before they're written to the EEPROM. Of course, some of them don't, such as this program memory signal here, or this program counter count, or the ALU-S signals. Those are all active high, so we don't need to flip those. Now, ignoring the ALU for just a little bit here, let's first have a look at this here, which is the input to our EEPROMs, which is the address. And so we have 13 bits on the address to our EEPROMs, and so they're numbered 0 to 12. And so the lowest 8 bits of that address will assign to the opcode of the instruction, which we're currently executing. So that's whatever the opcode is, a move or an add or a jump or whatever. And then the next 3 bits, bits number 8 till 10, will assign to the particular micro time that we're currently executing. So micro time 0 and 1 will be the fetch cycle, and on micro time 2 up until possibly micro time 7 will be executing whatever this opcode corresponds to. And then finally, the bit positions 11 and 12, this bit 11 we've wired directly to the carry flag. And then bit number 12, we had some combinational logic which will finally route any of the other 3 flags to our EEPROMs if the instruction is supposed to listen to that flag. So we had a look at that logic in the last episode, and so that allows us, in fact, to multiplex this last address signal with all of the other flags which we have in our flags register. And so these 13 bits, they constitute an address into the EEPROM. And so I've written a small macro here, which takes the various components that we're dealing with and in fact builds that 13-bit number together using binary operations. And so what we need for uniquely determining a particular address in the EEPROM is, of course, the opcode, for which we're writing microcode. Whatever the state of the carry and the flags bits are, so does this, in the end we're going to be writing a signal word at that address, does that correspond to the state where the carry flag is set or not, or does it correspond to the state where the flags are set or not? Then the particular micro time that we're dealing with, and so those 4 inputs, that's the flags, the opcode and the time, we combine those together, so the opcode is already, will simply go to the lowest significant 7 bits. To be safe, I probably could have ANDed that here with a maximum 8-bit value. But in general, this code generates its opcodes using other macros anyway, so I'm pretty confident that that should be fine. Then we take the whether we have a carry or not, and so I've defined a constant here. So the position of this carry flag inside the address is position number 11, so a 1 with 11 zeros in binary. And so we set that if this opcode, if this carry binary input to the macro is set. And so for the flags we do something very similar. So if that bit is set into the input to our macro here, well then in the output word that will result in this flags address bit, this bit number 12 being set. And then the last input here is the micro time, and so the micro time, we need that to go from bit positions 8 till 10. So we simply take that value, which is some value between 0 and 7, and shift it left bitwise by 8 bits, so we'll hopefully move it into that correct position. And so by ORing all of these pieces together, we can construct the complete address in the EEPROM where we want to write a signal word corresponding to a particular opcode, a particular combination of flags, and a particular microtime. Now, hopefully you'll remember from our discussion about the instruction register, when we had a look at how we want to build our opcodes, that if we ignore the ALU for a short moment, then we divided all the other instructions of our CPU into 3 broad classes. And so the first class was the move class, which basically just transfers values from one register to another. And we indicated that by setting the highest 2 bits of our opcode to 0. So any opcode that starts with 0, 0 is a move type instruction. And we designated the top 2 bits 0, 1 as a load instruction. So that will take a value from memory pointed to by a particular register and then load that into a register. And then the last class was the store class of instructions, which we designated by setting the most significant bits of our opcode to 1, 0. And so in that case, we'll be taking some register value and we'll be storing it into memory pointed to by some other register. And so in any of those instructions, we set the final 6 bits. We divide them into 2, and we set 3 bits for the destination register and 3 bits for the source register. And so we devised an encoding so that we can encode the 6 physical registers, which we have, into those 3 bits. And that left us with 2 combinations of 3 bits, which we could use to designate some special meaning. And so we'd said we'll assign the value 110, which corresponds to 6, to the fact that we're addressing the stack pointer register, but at the same time want to increment or decrement it, and we'll be using that to implement push and pop instructions. And we'd said that if we set that register destination or source to 111, then what we're actually referring to is an immediate operand rather than a register value. And so using such combinations, we are able to define a whole series of instructions as belonging to one of those 3 fundamental classes. So for example, the pop instruction is in fact a load instruction, 0, 1 here, and the destination register is B, which is what we're popping into, but we're popping out of not really just the stack pointer, but the stack pointer plus this the fact that we then subsequently want to increase the value of the stack pointer. And so we use 1, 1, 0 rather than 1, 0, 0 to indicate the stack pointer, and so that will translate in fact into a pop instruction. And so for the push we had something very similar. So this is in fact a store instruction from the D register, which we assigned value 0, 1, 1, into the stack pointer, which normally would be 1, 0, 0, but then by using this 1, 1, 0, we're saying, okay, and in addition, I want you to decrement the stack pointer as well as part of that operation. And so that would allow us to include also the push instruction as an instruction in the store class of instructions, beginning with bits 1, 0. Then we had this data instruction here, which loads an immediate value from embedded in the program into a register. That is actually a move instruction. And so the destination register is the B register, which we encode as 0, 0, 1. But then the source register isn't any of the actual registers on our computer, but is in fact this special value 1, 1, 1. And so that allows us to encode the fact that we want to get the value not from a register, but from the next byte in the program. And so this 12 here, this immediate operand, is in fact located inside the program. And so by doing that, we were able to encode this data instruction as a move class instruction. And so the first bits are 0, 0. Now here's another kind of a store where we're storing to an address which isn't pointed to by a register, but is pointed by an immediate address. So we're storing into some fixed part of memory. So that too, in fact, is a store instruction. Jump instruction to a fixed address is in fact a move instruction into the program counter, or if you like, a data instruction into the program counter. And so the destination register is a program counter. And so a jump is in fact also a move class instruction. Then a call instruction is in fact a push instruction onto the program counter. So we're storing the program counter on the stack and then jumping to some location. We'll see the details of how that works in a minute. But in our encoding scheme, that works out to be a store instruction with bits 1, 0. And a return is in fact go and read the jump address from the stack. So that means a pop from the stack directly into the program counter, so that then subsequently execution will start at whatever the address was on the top of the stack. So that's a pop instruction, which is in fact a load instruction. It's a load class here. And then finally, we define the no operation is in fact moving from the A register into the A register, and very neatly and conveniently, that turned out to be the opcode of all zeros. But so that too is in fact a move class instruction. So using that opcode encoding scheme, we can actually write C code here to perform that. And so we can define a number of constants here. So these are the three classes of instructions. So in binary, that's 0, 0 for move, 0, 1 for load, and 1, 0 for store. And so those will end up in the most significant bits of our opcode. And then we have these various register encodings, these 3-bit values, which we can assign to various registers. So we have all of the physical registers, A, B, C, D, stack pointer, and program counter, up these values. And then we have these special indicators. So this is the stack pointer plus an increment or decrement, which we encoded with a 110, and then an immediate operand, which we encoded with 111, all in binary, of course. And so using those constants, we can define how to build an opcode. So an opcode is of a particular class, so that's a move, load, or store, has a destination and a source register, which are 3 bits. And so we can combine all of those together. The source register comes to bits 0 to 2, so those are already in the least significant position. Then we shift the destination register to the left 3 bits, so they come to the left of the source register. And then finally, the highest 2 bits of the 8-bit opcode are in fact these 2 bits here, which indicate the class of instruction. So for all instructions except for the ALU instructions, we can actually encode the opcode using this macro. And so we don't need to calculate these values every time we want to talk about a particular opcode. And of course, the opcode itself is an important part of the final address of the EEPROM, which we calculate using this macro here. And so very quickly, before we get into the actual heart of our microcode, here are 3 more auxiliary functions which we'll be using a lot. So this one flips all the active low signals. So once we've built up the word of microcode, which consists of the 32 bits of control signal here, then before we actually write to the EEPROM, we of course need to remember that all of these signals which are active lows, we actually have to invert them. And so we do an exclusive OR in all of the bit positions which correspond to active low signals of the value which is coming in. So this value which is coming in is in fact simply an OR of a set of these constants. So they won't take into account whether the signal is active low or active high. So it'll in that bit position there will be a 1 if and only if we want that signal to be active. But of course that's not exactly what we'll be writing to the EEPROM. What we need to do to write to the EEPROM is to then flip all of those 1s into 0s and 0s into the 1s only in those positions which correspond to active low signals. So this is simply a huge OR of all of the signals in here which have an underscore. And so that will be one of the last functions we call before actually writing to the EEPROM. And then finally here we have a few convenience macros. So each of our 6 physical registers has 2 corresponding enable and write signals. And very often in our code we'd like to find the enable signal which corresponds to a particular register, or the write signal which corresponds to a particular register. So that's easy enough. I mean we only have 6 of them, so we have a huge switch here. And for example, for the C signal, well, the enable signal is the register C enable signal, and the write signal is the register C write signal. And so those 2 are convenience functions which we'll be calling from our code. And so we come to some actual microcode here, which we can now express using all of the work and all of the definitions that we built up here. And so microcode for any particular instruction is in fact a set of 8 different 32-bit signal words that, or maximum 8 32-bit signal words which we need our control unit to apply. And so that's what an instruction is at the end of the day, is a set of control signals that we need to send in sequence corresponding to one of 8 possible microtimes. And so in the most general sense, to implement a particular instruction, we will need 8 different sets of control signals, i.e. 8 different signal words, 32-bit signal words. And so in general, as we've been saying the whole time, the first 2 of those signal words are absolutely fixed and should be the same for every single instruction that we encode. In fact, they should be enable the program counter and write it into the memory address register. And then the second word should read from memory, which will be pointing to whatever the memory address register pointed it to, i.e. the program counter. Make sure we're accessing program memory. and then write that into the instruction register, and at the same time increase the program counter, so the CPU is ready for the next instruction when this one is finished. And so those two first signals of any microcode for any instruction, they're always the same. We'll never change them ever. And then starting from the third up until to the 8th position, so positions 2 and 7 in this array, well, those will actually implement a particular instruction after it's been loaded into the instruction register. And so in the most general case, when the instruction doesn't do anything, well, all we'll do is we'll reset the timer, so we'll do that immediately. And so that instruction will in fact do nothing at all. And so here now I've defined another series of functions which allow me easily to encode various lengths of microcode. So some instructions will have actually no microcode at all. So all they'll do is fetch, and that'll be the end. For example, the no operation instruction, all that needs to do is fetch and then do nothing. And so the microcode at position 2, which is at this position here, should contain this default value. All it does is reset the timer so it can start executing the next instruction. And all of the subsequent bytes, well, we set those to 0, just to make sure nothing happens, but they'll never actually be read because this signal will reset our counter, our internal control unit counter, and so we'll never actually be accessing any microcodes beyond there. But we might have instructions which in fact take exactly one piece of microcode apart from the fetch cycle to execute. For example, a move instruction from one register to another. In the beginning of the video we saw a move from one register to another, and so we had to fetch the instruction. Once it was fetched, all we had to do was enable the source register and then assert the write signal on the destination register, and that was it. And so we can do that, but of course we also want to at the same time reset the timer, and so we OR that so that whoever is using this macro doesn't need to remember to write that in the last bit of signal here. And once again, all of the other codes will actually never use them, so we set them to 0 here, but really the value is irrelevant because we'll never reach that point since we're resetting the timer at this point. And similarly, we can define instructions which might take 2 microcode cycles apart from the fetch cycle. So once again, we start inserting our first custom signal word at position 2, and then the second custom signal word, which is an input to the function, will go to position 3 here, and of course again we'll be at the end of the instruction asserting this reset timer signal, and so this instruction will halt after 4 cycles, so after cycle time 3 is complete. And so cycle 4, 5, 6 and 7 are all set to 0. Similarly, we have 3 length instructions and 4 length instructions, and so it turns out that on my computer I don't actually have any instructions which take 8 cycles. The maximum is 6, so I have 2 for the fetch cycle and then 4 custom cycles here. So now let's actually write some microcode to our EEPROMs, and so that's what this function here does. And so microcode is in fact is an array of 32-bit signal words, and so each element in that array corresponds to a particular microtime at which those signals should be asserted. So when we want to write to the EEPROM, we'll just loop through all of the possible microtimes from 0 all the way up to 7. And for each of those microtimes, we'll go and get the exact microcode that we're interested in. So that's here. Now, the microcode signals which we've written in here are all active high, and so they will only have 1s in their bit representation for those signals which we want asserted. But of course, before we write to the EEPROM, we need to remember to flip those signals around, which are in fact active low in our hardware. And so we looked at a function to do that earlier on, and basically it's all those signals which start with an underscore. So we do that, and then of course, well, we're obviously writing bytes to our EEPROMs, and in fact we're only ever programming 1 EEPROM at a time, and we have 4 of them, and of course our programmer can only program 1 single EEPROM. And so we need to run this program once for every EEPROM of our control unit. And so up here we have a constant, and so you can set that constant to whichever EEPROM you're actually programming. So here it's been set to program EEPROM number 3, but if we wanted to program EEPROM number 0, we'd set that to 1, or we can set it to 1 or 2, or whatever. So let's suppose we're programming EEPROM number 3. So what that means is that, in fact, we're only interested in these bits. These are the 8 most significant bits of our signal word. And so in our function to write here, once we've worked out and flipped all of the active highs, all of the active lows around, then we actually need to extract the 8 bits that we're interested in for the particular EEPROM that we're writing to. And so that's an input parameter into this function, but at the end it's just that defined constant which we have at the top of our program. And so when we know that, we can in fact shift this 32-bit value to the right. In this case, for EEPROM number 3, we'll shift it to the right by 24 positions. And so in fact we'll cut off the 24 least significant bits from this control word, and we'll be left with the 8 most significant bits, which are exactly the bits that we want to write to EEPROM number 3. And so that goes into this byte. Now if we were programming EEPROM number 1, for example, well then we'd shift this 32-bit word to the right by 8 positions, and so the least significant 8 bits would be cut off, and would be left with the 24 most significant bits. Now we don't want to write all 24 to EEPROM number 1, we only want to write the 8 least significant of those 24 most significant bits. And so we actually want to cut off the 16 most significant bits of those 24 most significant bits. And so that's why we have this AND with this is in binary, this is 8 ones. And that expression will calculate the exact 8 bits that we want to write to this particular EEPROM. So right, here we have it. We have the address and we have the byte which we want to write. So all that's left to do is to actually call the write function in our EEPROM library. And so we do that here. Now we can forget about that part. That's just a check which I wrote while debugging this microcode program to make sure that we actually write every instruction. But that's off in general, so we don't need to worry about that. Now, of course, all of this here depends on a particular carry flag and a particular other flag's value, which is coming in, because we use those as part of the address. Remember, those are inputs into our EEPROMs, carry flag and other flags. Now, the vast majority of our instructions, obviously, are not conditional and should be written for without conditions in mind. So in fact, what that means is we want this same microcode to be executed for all possible input carries and input flags values. And so in fact we want all of this to be done 4 times, once for every possible combination of the carry and the flags input. And so this here, write instruction, is in fact a write unconditional instruction for a particular opcode with particular microcode in a particular EEPROM number. What that needs to do is it needs to do it all once for the false, for a carry flag value of false, and once for a carry flag value of true. And so for a carry flag value of false, it needs to write it once for a flag's value of false and once for a flag's value of true, and the same for a carry flag value of true. It needs to also write it for flag is false and flag is true. So in total, we'll be writing that same microcode 4 times, once for each of the combination of these flags. Now that we know how to write microcode for particular instructions, all that's left to do is to actually do it, to encode all of our instructions. And so for each of the 4 classes of instructions that we have move class instructions, we have load class instructions, we have store class instructions, and finally we have ALU class instructions. For all of those, I've defined a global method which writes the microcode for those instructions into the EEPROMs. And so our main program here, our setup function, which is run once, we'll do some initialization, just this same check here, which we have to make sure that we actually want to run the program. Reason for that is the same as in the digital display. When you first insert the programmer with an EEPROM chip into the serial port, the program will start running immediately. And so to make sure it doesn't start overwriting whatever's there without us knowing exactly which program was still in the Arduino, we make sure that all of our programs prompt first on start whether you want to run them or not. So we have that little check in here as well. But so if we say yes, we should continue, then we actually do the work. And so that consists basically of running each of these 4 write instructions, or write functions, which writes a complete class of instructions into our EEPROMs. And at the end, if we want to, we can dump the contents. And then there's this, once again, this coverage check, which we can ignore for the moment. Now you'll notice that each of these 4 methods or functions has a conditional if around it. And so I can define at the beginning of my program which classes of instructions I want to write to the EEPROM. And so you might wonder, why don't I simply write all the classes? Well, as it turns out, the Arduino Nano, which I have, and which I use to perform this programming, doesn't really have enough memory to be able to handle all 4 of those functions reliably. And so not only are there conditional instructions here, but there are also these same conditional defines around the definitions of the functions. And so unless I've defined, for example, the ALU instructions in the beginning of my program here, that entire function will simply not be included in the program. And so by dividing that into 4 blocks, I actually generate Arduino code which can be executed. Otherwise I'd be running into memory and things don't work properly. So that's why I've divided that up. And so the way it's set up right now, it's in fact going to write the move class instructions into EEPROM number 3 when we run this program. So here is the code which will actually write the microcode for the various types of move instruction into our EEPROMs. And the most straightforward type of move that we have is a real move from one physical register to another physical register. As you'll remember, we encode those by saying 0, 0, and then whatever the destination register encoding is, and then the source register encoding. And the microcode for such an instruction is very simple. So we have the fetch cycle, which is fixed for all instructions. And then the first instruction dependent and only instruction dependent cycle, which is why we use this microcode 1 macro, simply enables the source register. So we have a control signal to enable the source register. And remember, we wrote a convenience function here to find out whichever the enable signal is for a particular physical register. And we enable the write signal for the corresponding destination register. And so that's all we need to do really for this move instruction from a physical register to another one. And so by looping over all possible source registers from A, B, C, D, stack pointer to program counter, and the same for all the destination registers, we can in fact write the corresponding microcode. Of course, moving from a register to itself it isn't a defined operation, and so in that case we don't actually write, and so we'll take care of those later. And so here, once again, very quickly, is an example of such a move instruction. So it's encoded as a 0, 0, which is class move, and then the destination register is 0, 0, 1, which is register B, and the source register is 0, 0, 0, which is register A. And so the microcode for that instruction on time t0 is it's a fetch cycle. So time t0 will get the program counter into there, and at time t1 we'll get the actual instruction into the instruction register. So that's the same for all instructions. And then time t2, which is the one that we programmed for the move instructions, well, that will enable, in this case, the B register, and then enable the A register, and set the B register to write. So we'll get that value into there. And at the same time, that's the end of the instruction. So our microcode 1 function added that signal to the final signal word, and so this instruction will end. And that's it. Now the next instruction, this jump instruction, is in fact a data instruction. And so we need to write into the program counter, and we need to write a value which is coming from the program, which is embedded in the program, which is an immediate operand. And so it's a move instruction into the program counter, which is register 5, and the source register here is 111. And so for this instruction we need a slightly different microcode. Of course, the first two values for t0 and t1 are always the same. Those are the two fetch cycles. And so now this instruction is in the instruction register. But the next part will be different. Of course, we need to write into the program counter. But the value we need to write into the program counter, we first need to go and fetch from program memory, because it's located in program memory at the next byte. And so the current value of the program counter has already been increased by the fetch cycle. And so that's now pointing, in fact, to the correct address. So we need to go and get this byte, which is this byte. out of program memory at this particular address. So the first thing we need to do is to get that value into the memory address register. And so time t2 for this data instruction will actually contain the program counter enable signal and the memory address write signal. And in addition, once we've done that, we'll need to want to increase the program counter once again, because if this weren't a jump but some other data instruction to some different register, well then we need to continue executing here. And so finally on this T2 we also need to assert the program counter count signal once again. And so this is T2 for a data instruction. So right, that goes into the memory address register. And now we can enable memory. And so this value will go out onto the bus from memory. And so that then goes into whatever register we're writing into with the data instruction. And so in this case, it's a write into the program counter. And we enable the memory. And so memory enable, and then whatever register we're writing to write, plus the timer reset, that's the control signal for time T3 for a data instruction. So we're on time T3 here. And so that will end this data instruction, which in our case, because it's into the program counter, is in fact a jump. And there it is. So as we just saw for the data instructions, which take an immediate operand, which is stored inside the program, just behind the instruction, which we want to write into some register. Well, we actually need two microcode. We actually need two instruction microcodes in addition to the fetch cycle. So we use our microcode 2 function here. And so on the first microtime, T2, we enable the program counter, which will bring its address out onto the bus, and that has already been increased by the previous fetch cycle. So that is now pointing at the piece of immediate data in program memory, and we write that into the memory address register. And at the same time, we increase the program counter once more, so that it will then point past the immediate data in the program memory to the next actual instruction. And then on the second time, T3, which is part of this instruction, we read from program memory, we enable memory here, and then we write to whatever the register is that this instruction is writing to. And so that is the microcode for the data instruction. Now we decided to encode the no operation and the halt instruction as move instructions as well, in this case from registers into themselves. So in the no operation, we said we'd encode that as a move instruction from the A register into itself. And so it turns out that the opcode for that is in fact 00 for move to the A register, which is 000, from the A register, which is 000. So an opcode of all zeros will in fact be the no operation. And so the microcode for the no operation it is nothing. And so we already defined this function here, microcode 0. So after the fetch cycle, we do nothing more. We simply reset the timer, and that's the end of the instruction. So if you remember here, we defined this microcode 0 function to have no custom microcode. So it simply resets the timer and jumps to the next instruction. And then the halt instruction, which is here, well, we need one control signal, which we need to assert, which is the halt signal. We have that signal. And so after the fetch is complete on microcode on microtime T2, we simply assert the halt signal, and so that's the end of that halt instruction. Of course, after that, the clock will halt, and so there is actually a timer reset in there, because this function also includes that in its signals, but that won't have, well, there'll be a falling edge, but that will be the end of it. And after that, the computer won't execute anything more, and so we will have to physically reset it in order to perform further operations. But that's the point of the halt instruction. Now, perhaps you'll remember from the previous episode that we talked about encoding these conditional jump instructions, and we have 4 of them because we have 4 flags. And so we encoded, first of all, the jump on carry instruction to some immediate address by hijacking the move opcode into an immediate register, because that makes no sense. And so we said, okay, we're not going to define any microcode for that. We can use this opcode for something else. And so we're using it for the jump carry instruction. And so in effect, this is the move into immediate from the A register, but we're assigning a different meaning to it. We're saying, okay, that corresponds to the jump on carry to some immediate address. And so this will be a conditional instruction. The microcode which we need to execute based on this opcode will depend on the current value of the carry flag. And similarly, we defined opcodes for the other flags. So for the jump on 0, the jump on negative, and the jump on overflow flag. All of them jump to some immediate address, and we all encoded them as move instructions into an immediate register, which by themselves make no sense. So we're reassigning those opcodes to the conditional jumps. And then remember that we only have one flag's input bit into the actual EEPROMs, and so we are setting that using some combinational logic based on an OR of ANDs of the actual flag with whether that flag is relevant for a particular instruction. So we're ANDing the 0 flag together with the 0th bit of the opcode, ORing that together with the negative flag and the first bit of the opcode, and ORing that together with the overflow flag and the second bit of the opcode, and the result of that OR goes into the flag's input bit into the EEPROMs. And so that's what will be available for us for defining the microcode. And so the microcode for this instruction will depend on whether that flag's input is 0 or 1. So for all of these instructions, the microcode in effect is the same. If the corresponding flag is set, then we jump, and if it isn't, then we don't jump. And so those are the encodings that we defined for our conditional jump instructions. So to write the microcode for these conditional jump instructions, so the opcode is in fact, it's a move class instruction into a destination register of immediate, which is the opcode that we're reassigning to these conditional jumps. And so the jump on carry, we said, would have all zeros as the last 3 bits. And so its microcode depends on the contents of the carry flag. So this we're not using the write instruction, but we're using this write carry conditional instruction function, which we looked at earlier. And so what that does is it takes into account the input of the carry bit. And so for a carry bit of false, it'll have some microcode, no matter what the flag's input is. And for a carry bit of true, it might have some different microcode. And so that's exactly the situation that we have here. So if the carry bit is false, then a jump on carry shouldn't do anything. So what in fact it does is it does increase the program counter by 1, because of course immediately following that instruction we'll have the address that we should jump to if the carry was set. But of course if the carry isn't set, we can't simply execute that as code, because it's not code, it's an address. So we do actually have to do one thing, which is to increase the program counter beyond that address which we're ignoring. But if the carry flag is set, then of course we need to execute completely different microcode. In fact, we need to execute more or less the same as a jump, which is an immediate into the program counter. So this microcode should probably be exactly the same as that. So we're enabling the memory address write signal, we're enabling the program counter output signal, and we're increasing the program counter, so that's the same as that. And then on the T3, which is the second custom microcode cycle, we're enabling program memory, and we're reading out this address that we want to jump to from memory, and we're writing, in this case, directly to the program counter. And so that's the microcode corresponding to the jump carry instruction when the carry is true. And now for the other conditional jump instructions, we don't depend on the carry flag, we depend on the input of that flag's bit, which is also coming into our EEPROMs. And of course that's coming indirectly from one of the other flags, which has been combined outside of our EEPROMs together with whatever bit is set in these final 3 bits of the instruction. But so the microcode is in fact always the same, and so we simply write it 3 different times. So this flag here, it could be flag number 0 or 1 or 2, so whichever one it is, that should result in these final 3 bits being either 0, 0, 1, if we shift 1 to the left by no bits, or we could shift it to the left by 1 bit, or we could shift it to the left by 2 bits, and so that will be either 0, 0, 1, 0, 1, 0, or 1, 0, 0. But no matter what it is, the microcode that goes into the EEPROMs is the same in every case. In fact, if the flag is true, which is this case, then the microcode is exactly a jump instruction, just as it is here. But if it's set to false, then we don't want to jump. Then we simply want to skip over the address that we're not jumping to. And so making sure that the correct flag is actually assigned to the correct instruction, that's not handled by this microcode. That's handled by this combinational logic, which we talked about in the last episode. Now, the reason we have two of these function calls here is, of course, whether or not to jump based on that flag bit is independent of whatever the carry bit says. So in both the cases where the carry bit is false or the carry bit is true, as long as the flag bit is false, then we should jump over this instruction. And so that's why we need to set both of these microcode sets, once for the carry equals to false and once for the carry equals to true. And of course we need to do the same for the case that the flag is true, in which case we do jump. And so that's how we encode our conditional jump instructions in our microcode. And so that basically concludes all of the different instructions which we've assigned to the move class, which have 0, 0 in their most significant 2 bits of their opcode. And any other possible combinations of bits in this move class are in fact invalid instructions or illegal instructions, or whatever you want to call them. And so we don't have exception handling or traps or anything like that in our CPU. So we can't really raise a trap signal or whatever it is as modern CPUs would do. So what we do is we simply do the same as halt, and we halt the computer on an illegal instruction. And so the illegal instructions, the ones which haven't been assigned any meaning, are in fact, in this case, moves with either a source or a destination operand, which is this stack pointer with automatic increase or decrease. We said we'd only support that for load and store instructions. And so if we ever encounter an opcode which is a move with this in one of its register operands, well, we consider that to be an illegal instruction. And so we have a microcode here which simply asserts the halt control signal, and that will be the end, and that will halt the computer. And the same here, we have some move instructions from a register to itself. So we assign specific meaning to the move from A to A and move from the program counter to the program counter, but any other register which is trying to move to itself, well, that's in fact an illegal instruction. So if it's a B, a C, a D, or the stack pointer, then we assign that the halt microcode. And so that, in effect, defines microcode for every single possible combination of bits in the opcode, where the first 2 most significant bits are 0, 0, which correspond to the move class of instructions. So here I've taken my EEPROM programmer, and I've in fact inserted EEPROM number 3 from the control unit into it. And so we can try and program EEPROM number 3 using our program. And so I've set the EEPROM number here to 3. And in fact, in this run, we'll be encoding the move instructions. So I've set that constant. And so I've hooked the Arduino here onto the serial port, or the USB serial port of my computer. And so we should be able to simply run this program. And so here is the serial monitor. And so it's uploading the program, and so now it's just making sure that that's what I want to do. And so we'll say yes to that. And then you'll see it's actually executing the code, which is writing the different microcode for the different micro times and different flags combinations into our EEPROM for all of the move instructions. So it's doing that for every register combination. And so as you can see, it's it takes a little bit of time to program those, and so we need to do that once for every instruction class and once for every EEPROM. So that's 16 times basically. Now he's done with the move instructions, so now the data instructions, of course there are a lot less of those. Then we're doing the special no operation and halt instructions, the conditional instructions, and then finally, as you can see, these are all the remaining gaps which we don't encode, and so we set all of those to halt. And that's it. That's a complete successful run of our microcode programmer.
Now I'll put a link to this microcode program here, which we run on the Arduino in the description of this video, so you can have a look at it at your leisure. Because this episode's been going on for quite a while already, we'll talk about the microcode for the load class, store class, and ALU class instructions in one more episode about microcode. So I'll see you then.